Hello. From audience side, if you have any question, you may please ask to presenter. Next presenter is Anjali Agrawal from IIT Delhi.
Is essential. Now, the problem with existing thermal simulators is that most of them use the finite element or finite difference based methods, which are quite slow and hence not suitable for complete analysis. The fast Green's function based methods also have a stage that requires FEM or FDM based calculations. In our approach, we have used the Green's function based methods, but we derive the Green's function using the simple polynomial expressions, and hence we avoid the slow or FEM or FDM based stage during the runtime. So to calculate the full system, to calculate the temperature profile of a chip, we need to solve the Fourier heat equation. Most simulators solve this equation using the FEM or FDM based methods. Another set of approaches used the faster Green's function based methods. Green's function is defined as the impulse response of a unit power source applied to the center of the chip. So in this method, we first obtain the Green's function of a chip based on its geometry and we store it offline. And we have the power profile of the chip. And during the runtime, we convert the Green's function with the power profile of the chip to obtain the full temperature profile. So we have created CFD models for our devices. CFD models are important for two reasons. First, the block specifications like the block parameters and material properties and placements need to be varied at during the initial stages of the design, which cannot be done in a real system. Also, to empirically obtain the Green's function of a chip, we need to apply a power unit power source at the center of the chip, which might not be practically possible in a running system. Hence, we create a 3D model and then we calibrate it against the real world IR camera images and thermocouple based measurements to obtain a three-way cross validated CFD model. So here's a brief overview of our compact thermal modeling approach. So first, we take the retail CFD model, which on which we have performed three-way validation, and using this, we obtain the classical Green's function for nominal block area and conductivity value. So using the classical Green's function and simple polynomial expressions, we obtain the component level modified Green's function. Now we convolve the component level modified Green's function with the respective power map to obtain the component level thermal profile. And then we superimpose all the component level thermal maps to obtain the full system temperature profile. Coming to the IR imaging framework we have used to validate our CFD model. First, we capture an IR image of the target device under different stress conditions. Next, we need to extract the per component power values under these stress conditions. Next, we need to pre-process the IR images to extract the thermal map. And finally, we validate our CFD model against these known power and thermal maps. So there are different power dissipating components in a system like the processor, RAM, flash, HDDs, etc. So these components can be broadly divided into two categories: compute intensive and memory intensive. So we have power values under. Next, we need to pre-process the IR images to extract the.
Audience are requested to please ask question from the presenter.